Hello, today I'm going to talk about tight dynamic problem lower bounds from generalized BMM and OMv. I'm Ce Jing, and this is joint work with Yinzhan Xu from MIT. In dynamic problems, we want to use some data structures to maintain some data, which could be graphs or sequences and so on. And this data is dynamically changing, so we want to support small updates to D, which could be insertions, deletions. And we also want to answer queries about D, such as graph connectivity. And the goal is to implement these updates and queries faster than the naive algorithms. Dynamic problems have been extensively studied in the literature, and we know that some of the problems can be solved very efficiently. For example, the dynamic connectivity problem in undirected graphs under edge updates. This problem can be solved in nearly logarithmic time per operation. However, some other problems appear to be very difficult to solve. For example, the same problem in directed graphs is very difficult. Currently, we don't know any polylog algorithms to it, and the best known algorithm runs in polynomial in n time. To better understand the complexities of these dynamic problems, it will be very helpful to prove some lower bounds on the running time per operation. However, unconditional lower bounds are very difficult to prove using current techniques. So people have started to use fine-grained conjectures to prove conditional lower bounds for these dynamic problems. And they can obtain higher lower bounds, which are closer to the best known upper bounds that we know. There has been a lot of work on using fine-grained conjectures to prove dynamic lower bounds, starting from the work of Padrashku and Abud and Vasilevska-Williams. And in the literature, there have been a lot of different fine-grained conjectures, such as threesome BMM, OMv, strong ETH, and APSP, and so on. And different conjectures are better for explaining different barriers. And among these conjectures, the most relevant to this work are the BMM and the OMv conjectures. Now let's look at their statements. In the Boolean matrix multiplication problem, we are given two n by n Boolean matrices A and B, and we want to output their matrix product over the Boolean ring. The naive algorithm for this problem runs in n cubed time, and the conjecture is that there are no truly subcubic time algorithms, combinatorial algorithms for this problem. Here, combinatorial algorithm is a notion that is not rigorously defined. Here it means algorithms that do not use fast matrix multiplication algorithms, such as the Strasson's algorithm. Currently, the best known combinatorial algorithm for BMM runs in n cubed over log n to the fourth running time. The OMv hypothesis was first proposed by Hansinger et al. In this OMv problem, we are given a Boolean matrix M and n vectors v1 up to vn, and we want to output their matrix vector products mv1 up to mvn, and we want to output them in an online fashion, which means that the next input vector only arrives after we have returned the answer to the previous vector. And here the conjecture is that there are no truly subcubic time algorithm for the OMv problem, even those algorithms that use fast matrix multiplication. Currently, the best algorithm for OMv runs in n cubed over 2 to the root log n time. These two conjectures have been very productive in proving various dynamic problem lower bounds. However, there still remain many other dynamic problems whose complexities are not well understood. One of the examples is the dynamic range mode query problem. In this problem, we want to maintain an integer array of length n, and we want to support insertions and deletions into this array. And each query is specified by two indices L and R, and we want to return the most frequent element in this subarray from AL to AR. This problem looks very simple, but it's very difficult to solve. Currently, there are no polylog time data structures known, even for the easier static version. This is in contrast to many similar looking problems, such as range minimum and range sum, range median. There are several folklore combinatorial algorithms for this dynamic range mode problem, and they achieve an order n to the 2/3 query time and update time. For the easier static range mode problem, we can achieve order n to the 0.5 query time after n to the 1.5 time pre-processing. And if we allow fast matrix multiplication, then we can achieve slight polynomial improvement to this running time. Now let's look at the fine-grained lower bounds for this problem. For the static version of the range mode query problem, we know a tight combinatorial lower bound. It was proved by Chen et al. In 2014. They showed that under the combinatorial BMM conjecture, there is no combinatorial algorithm that can achieve better than square root n query time and better than n to the 1.5 pre-processing time. So essentially, this means that if we want to improve over the square root n time algorithm, then we have to use fast matrix multiplication. However, for the dynamic range mode problem, we don't know any tight lower bound. We do know that the previous combinatorial lower bound can be strengthened into a non-combinatorial lower bound under the OMv conjecture. However, the exponent still remains 0.5. So it could be possible that there is a combinatorial algorithm for dynamic range mode in square root n update and query time, but we don't know them. In our work, our new result says that this is impossible. We show that no combinatorial algorithm can solve dynamic range mode in better than n to the 2/3 query and update time and any poly m pre-processing time. So essentially, this means that the folklore combinatorial algorithm has tight exponent. Our result is based on the combinatorial four-click hypothesis. It says that there is no combinatorial algorithm that can detect a four-click in an annual graph in better than n to the 4th running time. This conjecture is stronger than the combinatorial BMM conjecture. And in fact, it can be seen as a generalization of BMM because BMM is known to be a fine-grained equivalent to the triangle detection problem. our proof for the dynamic lower bound used some ideas from the proof for the static version by Chen et al. And in fact, our proof strategy follows the following pattern. We start from a reduction from k-1 click to the static version of this problem, and we modify it into a reduction from the k-click problem to the dynamic version of this problem. Here, the intuition is that we can efficiently enumerate the extra vertex in the k-click using the dynamic operation of the problem. Using this proof strategy, we can obtain tight combinatorial lower bounds for more problems. For example, the dynamic 2D orthogonal range color counting, the dynamic D-dimensional orthogonal range mode, and the dynamic two-pattern document retrieval problem, which is a text preprocessing problem. And so on. And we believe the main takeaway of this set of results is that the combinatorial k-click hypothesis is very useful for proving dynamic lower bounds. Previously, in the literature of dynamic lower bounds, they mostly used the k equal to 3 case, which is the BMM conjecture. And for larger k, it was not very popular. The only exception we know is a region reduction from 4-click to dynamic shortest path. And in our work, we have a more systematic way of proving dynamic lower bounds using combinatorial k-click conjecture for larger k. Now let's look at the second part of our talk, which is about the dynamic subgraph connectivity problem. In this problem, we are given a static undirected graph G with M edges. We preprocess it, and then we want to maintain a dynamic vertex subset S. We support insertion and deletions in S, and each query is specified by 2 vertices U and V, and we want to answer whether U and V are connected in the induced subgraph by S in G. This problem has a combinatorial algorithm by Chen, Padrashku, and Rodity in Fox 2008. Their update time is roughly m to the 2/3, and the query time is m to the 1/3. More precisely, their result gives a trade-off between the query time and update time. We can reduce the query time by increasing the update time, and the product of query time and update time is equal to m. The lower bound for this problem was also studied before. There is another trivial algorithm that simply runs a BFS for each query. Previously, the lower bound was studied by Yinzhan et al. So they ruled out this orange region by the OMv conjecture. So this means that the product of the query time and update time has to be at least m, and the exponent cannot be improved to better than 1/2. However, this question mark region is still open. The main question is whether we can improve this 2/3 exponent in the update time. For example, can we get a algorithm with square root of m update time and query time? And our new result says that this is impossible for combinatorial algorithms. We show that no combinatorial algorithm can achieve better than m to the 2/3 update time and greater than m query time, given any polynomial time preprocessing. And again, this is based on the combinatorial 4-click hypothesis. So this means that if we want to improve the chain pathological quality algorithm, then we have to use fast matrix multiplication. Now let's look at the third part of our results. We have seen that the combinatorial BMM hypothesis has a k-dimensional generalization, which is the combinatorial k+1 clique hypothesis. We have also seen that the online version of BMM, which is the OMv conjecture, can prove non-combinatorial lower bounds. So now it is very natural to propose a new fine-grained conjecture that fits into this diagram. We call this the OUMVK conjecture. It can be seen as a k-dimensional generalization of the OMv conjecture. Here, let's state the OUMVK hypothesis. We are given a subset M of several k tuples. Each coordinate is from 1 to n. After the preprocessing, we want to answer n queries online. Each query is specified by k sets, U1, U2 up to UK, where each set is a subset of the integers from 1 to n. And we want to answer the following question. Is this set non-empty? In other words, does M contain a k-tuple such that the ith coordinate is inside the UI set? And our conjecture is that we cannot solve this problem faster than the brute force algorithm, which runs in roughly n to the 1 plus k time. So this hypothesis is a natural generalization of the OUMV hypothesis proposed by Hanzinger et al., which is equivalent to OMV. And their OUMV hypothesis is the same as the OUMV2 in our notation. And we will show that this OUMVK hypothesis is very useful for proving dynamic geometry problems lower bounds in k-dimensional space. And usually we can obtain higher lower bounds as the dimension k increases using the OUMVK hypothesis. Now let's look at, sorry, I forgot to mention that this OUMVK hypothesis holds for algorithms that can use fast matrix multiplication. Now let's look at one example, which is the dynamic skyline points counting problem. We want to maintain a set P of n points in d-dimensional space. And we want to support insertion and deletion. And for each query, we need to answer how many skyline points does P have. Here, a skyline point of P, or we can also call it a maximal point, it's defined as a point such that there is no other point y in P that dominates x in all the d coordinates. A result by Chen in 2003 gave a semi-online algorithm for this dynamic skyline points counting algorithm, the dynamic skyline points counting problem in 2k minus 1 space with update time roughly n to the 1 minus 1 over k. Here, semi-online means whenever a point x is inserted, we are also told when in the future this point will be deleted. So this is easier than the fully dynamic setting. And our result says that This running time is tight under the OUMVK hypothesis. So we can see that the complexity of this problem increases when K increases. Our OUMVK hypothesis also implies many other tight lower bounds. For example, the chance half-space problem in K-dimensional space, the K-dimensional Erikson's problem, and also the K+1 dimensional Langermann's problem, and so on. Okay, conclusion, we used a combinatorial K-clique hypothesis and the OUMVK hypothesis to prove tight fine-grained lower bound for dynamic problems. Now let's mention some open questions. First, can the dynamic subgraph connectivity problem have update time better than m to the 2/3 using fast matrix multiplication? Second, what is the optimal update time for dynamic skyline points counting in even dimensions r to the 2k? We allow semi-online algorithms. Our results only resolve the complexity for odd dimensions. So it's an open question, what's the correct complexity in even dimensions? Thanks for listening.